All right. So let's find the expressions for alpha and A and the rest of these, and then we'll do another example. Okay, so this rod, uniform mass, is going to be rotating about the pivot, and we are to find the angular acceleration and the linear or translational or tangential acceleration. Since there's a pivot, there's a force about a pivot, that implies that there's a torque. So we know that torque is equal to force times the radius. And the radius in this case is going to be the distance where the force is applied, which would be the L/2 or length over 2. So the force at the center of mass here is going to be applied at distance L/2 from the pivot. So that's your R in this case. And we also know that since there's going to be a motion about the pivot, it's not going to be static, so it's going to be also equal to moment of inertia times alpha. So what we want to do here is easily we can solve for alpha, and then from there we can solve for A, because A is equal to R alpha. So the force in this question is going to be mg, the distance where the force is applied from the pivot, L/2. Moment of inertia of the rod is 1/3 ml squared, times alpha, and we can solve for that. So what we have, mg L/2, 1/3 ml squared. The m's cancel out, right? One of these L's cancels, and so we're left with alpha equals to 3/2 g divided by L. So that's the angular acceleration of the rod itself. About the center of mass. Any questions on that part? So as you can see here, we're left with, just cut out the middleman, so g divided by 2. And this is going to be L/3. So 3/L. Cancels those guys out, and so we're just left with 3/L. Let's get that. All right. Therefore, the linear acceleration of the system now we got to be careful when we're trying to talk about linear acceleration. Are we talking about the linear acceleration of this mass point, any mass points? Because the linear acceleration is going to be contingent on the distance a particular mass is from the pivot. So the linear acceleration at this point is going to be different from the linear acceleration at this point. And it's actually going to be double at this point versus the center of mass. How do we know that? Because in terms of rotations, linear acceleration is equal to radius times alpha. So depending on what mass you're talking about, you have to take into consideration its distance away from the center of rotation, or the axis, the hinge point, the pivot. That radius, that distance r, and multiply by alpha. We have alpha already. We're talking about the linear acceleration of the center of mass. So we have the radius, which is L/2, right? So I'm going to do it this way, and of course, I'm going to conform to what we see via the example. So if we were talking about the center of mass itself, this distance will be L divided by 2, and the angular acceleration is what we just found, 3/2 g divided by L. So that is my angular acceleration, cross out my L's, and I get 3/4 g. That's just at the center of mass. But the question in the example is, what's the linear acceleration of the rod? So we have to consider the extreme point of the rod, which is distance L, and multiply that by alpha, and we get 3/2 g. So this is this, like the center. This is the entire rod. This would be L times alpha, which is L 3/2 g. And as you can clearly see, that the linear acceleration at the extreme is greater than the center of mass, than the linear acceleration at the center of mass. Center of mass is 0.75, and this is 1.5 times gravity. All right, units check out, meters per second squared. It's in terms of g, all good. Okay, so the next thing we want to find is the velocity at the bottom. So what we can do in this part, we can approach it in one of two ways. We can approach it using energy principles, which is generally easier, or we can use kinematics. We should get the same answer. Thing with kinematics, it can get a little cumbersome because we're going to be doing an arc length, or we could do a distance L over 2. It's all how we look at it. I'm going to approach it from energy principles. And that's something that's we're going to be talking about a little bit today if we have time. Not, it'd be next class. So I'm going to use energy conservation. It's much easier. If you want yourself, you can turn to page 290, and I'm just taking the same example. So energy before, the symbol for gravitational potential energy being U, KF plus UF. Now, of course, the rod is in the air. At the beginning, the initial velocity is 0, so all of the energy in the beginning is potential energy. So we'll have, from the center of mass, we'll have mg L over 2. L over 2 is the distance above the 0 point. That's the halfway point. So it's like, when we had that hemispherical bowl, and we had, I think it was, we had a pivot point here, and we had distance r, and we had to figure out for this particular mass what the speed was at the bottom. Well, the height is just going to be the radius. And the radius in our case here, with respect to the center of mass, is just L over 2, the length L over 2. So it's the same idea here. So we're looking at the speed of the center of mass. Or we can look at the speed of a point at this point, distance L. It just depends on what the problem's asking you. So we're just going to find VF of center of mass, the final speed of the center of mass at the bottom of the swing, right? So this is potential, kinetic is 0. And now at the bottom, what we have is we have a rotational kinetic energy. there's two types of kinetic energy that we can consider. We can have, let's say if we have a wheel that's spinning about its axis and moving forward, we're going to have linear kinetic energy as well as rotational kinetic energy. But in this case, since we just have the rod spinning about its pivot, it's just rotational. It's not moving forward, right? So we just have the rotational kinetic energy to consider only. And if you recall, rotational kinetic energy is 1/2 moment of inertia omega squared, and so at the bottom it's be at ground zero, so the final potential energy is 0. But we need to get that, so we can extrapolate V final from omega. So we have I, and we know that omega is just going to be V final over the radius, which is L/2. And so we can solve for V final. And we know what the moment of inertia is. We can put that guy in there and cancel out our M's and all that stuff. Okay, 1/3 ml squared V final over L/2 squared. So did anybody get that already? M's cancel out. If you do it properly, you're going to get the the same result as you see in your textbook. But I think they just solve for they solve for angular velocity, but same idea. This is angular velocity. We're using it to solve for the linear speed at the bottom. This will be GL/2. These L's cancel out here, goes away. 1/6 the final squared over 1/4 squared, or 1/2 squared, which is 1/4. We want to get rid of this fraction, so we just do times 4. So we have GL/2, which is and that's just 2/3. So we can just do, and then when we reciprocate this, it becomes 3/2. All right, because this is just 2/3. We want V final to be by itself, so we just reciprocate. So that's GL/2 V final squared, and pretty much done. So that's going to be 3/4 GL, and that's our final speed at the bottom. Any issues on that? Questions? Yeah. And you can even check your units, like if you need outs, so that's going to be special. I mean, at least the units check out, because this is going to be meters squared per second squared, and then the square root of that is meters per second, which is the units of velocity. So at least the units work, and the maths seem to check out. It's a nice problem because it's a precursor to what, we talk about energy conservation principles with rotating objects. Rotational kinetic energy with linear kinetic energy and potential energy, which doesn't change. And just to repeat, we're trying to find the velocity of the center of mass. Okay, so we're at L over 2. We're trying to find that, in which we found what we could also find the velocity of a point at L. So it all depends on your reference. Any questions on that? Okay. So next, what we want to do is find the expression for rotational kinetic energy. Who actually did that one? Now, I gave you the formula for it, but that one should be okay. So the next thing we want to find is just a simplified expression for rotational kinetic energy. Who wants to volunteer for that? I actually just kind of did it, but did anybody get that one?
I got 1/12 mg
Yeah, your mic
squared times squared.
Okay, did you substitute the moment of inertia expression for I? Yeah. Okay, so since Mike is having little issues, but I'm just going to write what I believe he said. So 1/2 moment of inertia, 1/3 ml squared. And then we have another question. No problem. No, yeah, it's technical. It's not your fault. So 1/2 times 1/3 ml squared, which is the moment of inertia. And then omega, we could leave it as omega, or we can put it in terms of this guy, or I don't know. Did anybody do that? Did we get to that part? You want to volunteer your answer if you got that part? So again, I'm just going to write this a little bit further over here. So 1/2 times 1/3 ml squared. And omega squared is, well, who can tell me besides Sin the formula for omega? Selena, do you have that? Not picking on you.
No, Mr. Kelly.
So what is omega equal? Just the basic equation for that.
Is it alpha over time?
Well, in terms of velocity. Yeah. But you're correct with that. So what Joya said is alpha over time. Alpha multiplied by time. So because what I think Joya you're implying is you're going back to the old school kinematics where we said velocity is a times t, but if we make that into angular velocity, be omega alpha time. But we're not going to use alpha in this case because we're not assuming that there's going to be a translational acceleration right away. We can transform omega in terms of v. Who has that? Okay, I'll help you out. Vt equals radius times the W looking thing, omega. And then we can make a substitution for omega. Don't be afraid to speak out, guys. Omega is V divided by R. And we substitute back in here. And so we'll have the translational speed divided by R squared because omega squared. So let's simplify that. Oh, okay. And then we have an expression for the final translational speed we just saw for that. So why don't you take this moment and simplify this using this expression for velocity. So I'm going to erase this part. I will write the preliminary expression and you guys can just solve it out. Yeah. Kind of messy, but you can do it. Take a couple of minutes to simplify that guy. If you haven't already. Yeah. Okay, so we got, in this case, would R be L or L over 2? We're still going to be working with L over 2. Yeah, because we're still keeping in context with the center of mass. Yes. So, yeah, good question. So, because you guys can leave it in terms of R, but since we're just talking about center of mass, let's leave R as L over 2. Good question. So, it keeps everything consistent. L's all over the place. So raise a hand or a question if you got the final expression. One thing you will do in this class, a bunch of algebra. Fine tune your algebra skills. Okay. Pregunta, question. Yay, okay. You too, Hernandez. Anybody get the expression? I know it's kind of hard to write, but anyway, just say I got it or something. I don't know. All right, 9 over 96 GML squared. Well, it should be in terms of mass times velocity squared. Okay. 0.5 mlg. Okay, let's see it. All right, so 1/6 ml squared. All right, this whole thing, square root of a square. You know, it's funny, like these so-called complex operations, that square roots and add and subtract. Gotta do that. Yeah, not really. You know what I mean? It's just G over L, and then This becomes L squared over 4. Squared everything. So just in case those of you are a little sketchy about the denominator, I'll just do the middleman for now. Okay, those go away, but we got to do the numerator, right? So we got rid of that. So there's another L here. He goes away. Okay, so there's a 3. Oh boy, this guy goes away. So 1/2, 3/6, 1/2 ML times G. Yeah, I think somebody got that. Yeah, 0.5 mLg. Yes, Lily. Yes. Perfect. Yeah, I mean, we see any questions. We see how that's just did all the substitutions, stuff like that. So this is our rotational kinetic energy term about the center of mass. That's a vital question. Are we doing the rotational kinetic energy about the center of mass or about the extreme edge? Because that does matter with the R, right? We're keeping in line with center of mass. Okay, we could do it about any point. Okay. So let's get a, I'm going to skip the rest of these parts, center of gravity, and just trying to occupy a little space here. So I think we can, the linear stuff, I believe we can handle that. I mean, we kind of have done that there, but maybe I'll come back to it next time. I do want to get to this next example. Okay. For this example, you want to go to chapter 10, number 77. I want you to find what they're asking for. This is yo-yo here. A string is wound around a uniform disk of radius r and mass m. The disk is released from rest with the string vertical and its top end tied to a fixed bar. Show that A, the tension in the string is 1/3 of the weight of the disk. The magnitude of the acceleration of the center of mass is 2g over 3, and so on. The speed is 4gh over 3, the square root of that. You show all those expressions after the disk has descended through distance h. Verify your answer to part C using the energy approach. So you don't have to do the energy approach for right now. You can do kinematics just to find final speed. But if you're game, go ahead and use conservation of energy. It descends a height h. So center of mass descends, well, should have just dotted this guy out. Anyway. All right, so that's a little cluttered. Keep it simple. Okay, so da 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 da. So the center of mass. So it's descended a height h, assuming that is h. So we have rotations and we have linear acceleration. So we're going to have a force equation or equations and a torque equation. But keep in mind that the torque provided by the string is going to be the force of the string as it pulls the yo-yo upward. If it's released from rest, the yo-yo is going to, fall down to the ground. But as it is with a yo-yo, you're trying to pull it back up, then the tension is going to cause the yo-yo to rotate counterclockwise. So if you pull it up in the direction of t, we have a counterclockwise rotation. I get that question asked all the time. No, it wouldn't, because imagine the yo-yo falling down just without the string. Well, it's on the string, but the string's not pulling, you're just letting it go. As you let it fall down from this position, it's going to rotate about this string in a clockwise fashion as it falls down. So it's going to, just trying to figure out a way to help you visualize, but so this is at rest. As it falls, radius r, originally here, is going to be here, then it's going to fall downward clockwise. But once you pull it up, it's going to go the other way, counter. Yeah, this is best demonstrated with a yo-yo with a piece of tape as R, and you can see the clockwise fashion. Try and take a moment to see if you can visualize that. I mean, if you're looking at the picture on in page 70, number 77, if the yo-yo would fall down, it's going to rotate, and so the position of R is going to go downward in a clockwise fashion as it goes down. Yeah, yo-yo. Okay, reverse pulley. No, yeah, it's more or less like a model of a yo-yo. Yeah, I get it. Every year it's the same question. It's uncanny, but yeah, it's the proper visual. Anybody prove it? All right, let's start this guy. So it moves down and has linear acceleration, and it's going to have angular acceleration about the pivot. So as it rotates, we're going to have angular acceleration about the axis of rotation, the center point, and it's going to fall down with a linear acceleration. So we have a force equation or two and a torque equation, because there's a force being applied. There's a force being applied at the radius. So let's get this guy going. Okay, I'd like to do that one. All right. So everything's in the vertical direction. So it falls down. So the linear acceleration is here. So tension is going the other way. So negative T mg, that equals ma, or ma sub t, for your tangential acceleration or linear acceleration, same thing. Our net torque equation is going to be tension times radius, force times radius. So the tension is the force, equals moment of inertia times alpha. And for a solid disk, keep that in mind for the shape, the solid disk moment of inertia is 1/2 mr squared. That's I. And the alpha would be linear acceleration divided by radius. So when these shapes are described, it's very important, because the moment of inertia will be relative to the type of shape it is. Is it a solid disk? Is it a sphere, hollow cylinder, thin spherical shell? So those things are going to matter for the moment of inertia expression. So this R cancels out here, and then this R goes away both sides. And so this is going to be T equals 1/2 mass times acceleration. But since in our force equation we have negative T, this is going to be negative 1/2 ma. Right? Negative T equals that. So then we substitute it back in, 1/2 ma. Get 1/2 ma plus mg equals ma. Ma is on both sides. Okay. Why does the r cancel out? Because this is going to be r squared, and then this is divided by r. So one of these guys goes away up top with the denominator. Because now we get to the other r, it's going to be tr equals 1/2 mass times r, because this r is left over. So r occurs on both sides, so you get rid of it, and the a is just left. Okay. Yep. So then it's, m's go away here, and then g is equal to a. But that 1/2. Sorry, it'll be, I already canceled that. So 1/2 a and 1, okay, so that's going to be 3/2. So acceleration is 2/3 g. So that was one of the parts. So, to prove that the acceleration is 2/3 g, or 2g/3. Yeah. So now we got this part. We can go and prove the tension, get the tension being 1/2. What is it? Or 1/3 the weight of the disk. So let's go back to our original equation, negative t in a. So we know that a is 2/3. And so this tension is going to be mg minus ma. Just swap the guys around. That's going to be mg minus 2/3 g. Okay, so that's just g minus 2/3. 1 minus 2/3, 3/3. You see that, so g's cancel out. I can factor out the g's. Doesn't really matter at this point. It's trivial. So 1 minus 2/3, which is 1/3 mg, and that's your tension. Anyone not get that? See how that's done. So once we get the acceleration, as we've done in all of our problems, now you can just go back and domino the rest: the tension, velocity, time. And obviously, speaking of the velocity, we can use kinematics to get the expression for the final speed. Okay. So VF squared equals VI squared d arbitrary, distance h, whatever. It's just some distance d that it traveled through. We have the expression for the acceleration. We know it started from rest, so that goes away. Two times 2/3 GD, and yeah, 4/3 GD, GH. It doesn't really matter at this point. So it's 4/3 and GH. So again, using these torque problems with linear forces, torques, you can use kinematics to get other expressions, because if we're talking about the the speed of either the center of mass or a point anywhere in this disk or whatever shape it is. You can use kinematics to figure out its speed, its acceleration, how much time it takes for a particular point to fall down, because all of these points with respect to the center of mass or including the center of mass can be related kinematically with your simple kinematics expressions for velocity, time, and so on, acceleration, and all that. Any questions on this part? Hopefully that was straightforward. I think the key is just figuring out how the system's going to rotate at the beginning, and then everything kind of dominoes. Okay. So the last thing I want to talk about today is section 10.9. And simplify it as much as possible, because there's a purpose for why you do anything, for why you want to explain it as thoroughly as that in section 10.9. See, in section 10.9, you want to explain it in such a way to show that if an object is rolling, it's rotating and rolling forward, what does it mean to have an object that's rolling without slipping, right? So the explanation given in section 10.9 is just helps you understand what's meant with something that's rolling without slipping. And if you have an object that's rolling without slipping, it has friction at the bottom of the surface. So you have a wheel on a surface and it rolls forward without slipping. There's an ample amount of friction going the other way to keep it rolling forward, well, without slipping. I'm going to simplify the argument in section 10.9. Talks about the rolling motion of a rigid object. So also this rolling without slipping, it never loses contact. We're going to keep things uniform. And it's just a condition to help us understand what the kinetic energy is going to be for, say, a sphere or a wheel rolling forward. So with this same wheel, we have the center of mass that's going forward. So we're going to have to consider the velocity of the center of mass as it translates forward. So you can just treat the center of mass as a particle. Like back in the day, we had a particle moving forward. It had this particular mass, velocity, and it had a linear kinetic energy, 1/2 mv squared. So it's the same thing here with the velocity of the center of mass. It's going to be translating forward, rolling forward. So if you have any point that's outside of the center of mass, it's going to be, well, rolling forward essentially, but it's going to be rotating about the center of mass. So there's going to be a rotational kinetic energy about all the points that is not the center of mass. So all of these points out here are going to have rotational kinetic energy, which is given by 1/2 I omega squared. And the center of mass here is given by 1/2 mv squared. So for an object moving forward or rolling forward, there's two types of kinetic energy. There is the linear kinetic energy, which is our standard 1/2 mv squared, and the rotational because it's spinning about an axis. And so that's basically it for the kinetic energy terms. So if I had an object at the top of a roller coaster, a sphere, solid disk, whatever it is, knowing its moment of inertia, I can find its linear velocity at the bottom by considering, understanding that it has a height h above 0 and it's rolling forward and down. It's rotating and moving forward, moving downward. So it has linear speed or linear kinetic energy as well as rotational kinetic energy as it rolls. Whereas if this was just a point mass, obviously we have a situation where it's just 1/2 mv squared. We're not considering any rotation. The radius of this object is going towards 0, whereas the radius here is much greater than 0, right? So we have two things. So the total kinetic energy of a rolling object, right, is, just given as rotational kinetic energy plus your linear. And so that's basically 1/2 the moment of inertia about the center of mass, because we typically take the standard or the basic moment of inertia is about the center of mass. So that's why we say ICM. But of course, there's certain times when we can calculate a new moment of inertia if we rotate the object that's not at the center of mass. But this is the basic case, 1/2 ICM omega squared plus 1/2 VCM squared. And you'll eventually get comfortable with just writing 1/2 I omega squared plus 1/2 mass velocity squared. But this is important to help you understand that all of these particles that have a radius from the center of mass are going to be rotating about that point. Hence this term for the kinetic energy. And this term here is just only relative to the center of mass as it moves forward. So think of, if you imagine, if you will, a bicycle wheel, and the center of the wheel is always just moving forward. It's not rotating. It's just moving like a point particle. But all of the other points about the center of mass are rotating at the same time. So that's the rolling motion of a wheel. So that's really the total kinetic energy of a rolling object. Right? If I want to take it a little step further, we'll be done for the day. So we have this term here, and we can transforming, we get the total kinetic energy 1/2 ICM. But this is moment of inertia about the center of mass. This is the particle at the center of mass moving as a point particle. Omega can be written as VCM over R squared, because V is R times omega. Omega is V over R, plus 1/2. And if we factor all the terms, and you don't have to do all that. It's just another way of writing the same thing as before. 1/2 a moment of inertia times omega squared. So think of this energy as the energy of all of these particles as they rotate about the center of mass. That's what's going on. And the center of mass is going forward like so. This red is for this term. All of these guys out here and all of the other guys that are rotating around have this type of kinetic energy. Any questions? And then potential energy is the same thing, mgh. Because it's always going to be, potential energy is going to always be with respect to the center, as most of these problems will be. in terms of the center of mass of the object. Okay, that's all I have. Is there going to be anybody here to make up any skills tests today?